But what I want to do, which I think might work better, is why don't I divide this by this? That'll give me a quadratic, and I already know what to do with quadratics. I can find my roots using the quadratic formula. I can find my other roots by factoring. So I'm going to do my division first. And I'm going to do it as a long division, or as a synthetic division. So 6, -5, -7, and 4. I write my coefficients, and I use the root. So I bring down 6, and I multiply it by -1. I add those, and I multiply it by -1. And I multiply by -1. Hey, my remainder is 0, but I now have 6x squared minus 11x plus 4. And I have two options here. I can try to factor this using the AC method, or, and I think what I would do is I would go, my last two factors are minus b plus or minus b squared minus 4ac over 2a. I think I would use the quadratic formula, and I find that my last two factors are x equals 1/2 and x equals 4/3. Which were in here. And this is going to be our main method of attack. For higher order polynomials, we will divide them down until we get them to quadratics. Once we have quadratics, we have a very quick way to get the rest of it. Plus, and this is really important, we're going to find out that they're not always real numbers. Sometimes imaginary numbers are hiding in there, and the only way to see the imaginary numbers are through our quadratics. Our quadratics will let us know when the imaginary numbers are popping out. So I told you they became useful. They help us find these. And so if I were to write this in its factored form, I'm going to just bring all of this up here in bright green. I have x minus 1/2 times x minus 4/3 times x plus 1. So let's look at this and go back and see what we had. So I'm going to go all the way up to the top here. I had this function. 6x cubed minus 5x squared minus 7x plus 4. The best I can say looking at it is these are all integers. So there should be rational numbers that come out of it. It should be at least one or two. At the most, I'm going to have 3 roots. And that's about all I can say just looking at this function. So I pull out the rational roots test and I say, hey, if there is some rational number that is a factor of this thing, it's going to have a numerator that is a factor of this and a denominator that's a factor of this. So I list all my factors of a sub n, naught. So factors of a sub naught. And I list all my factors of a sub n. And I put them together as a fraction. I will repeat over and over again because I mess up signs. Me. You've noticed it. You've caught it. Seem to all of these get the plus or minus. Because the way factorization works, I could be multiplying by the negative times a positive times a positive, or a negative times a negative, right? The signs here aren't going to tell me much yet. We're going to have some more tests that are going to tell us how many positive or negative roots we have. Tell us how often we dive up and below the x-axis. But for now, this says, hey, here are your possible answers. Now I have to find them all. Now I could go through and I could plug every one of these numbers into this function. And all the ones that return a 0 would be my answer. So I could go back in and I could plug in 2, positive 2, and I'd find I'd get a remainder. I'd plug in a negative 2, I'd find I'd get a remainder. I could plug in a positive 4, and I find I'd get a remainder. I'd plug in a negative 4, and I would find that I'd get a remainder. I'd plug into a positive 1/2, and I wouldn't get a remainder. I could plug in a negative 1/2, I would get a remainder. I could plug in a positive, and you just go through and you could do this 16 times. We're going to try to be smart about it, and we're going to try to reduce our polynomial. And this is where synthetic division speed really comes in handy, is once you have found one factor, I can take this third degree polynomial and doing my synthetic division, I reduce it to a second degree polynomial. If this was a fourth or a fifth degree polynomial, and I reduced it down to a lower degree polynomial, I would not have to go through and recheck all of my P's and Q's. Right? Mind your P's and Q's. Right? I would have the list I had before, because that was still possible for the larger polynomial, and so the smaller polynomial is going to be made out of those things. You notice if we plug these in and run through and do the quadratic, which I went through quickly because we have discussed this, but if you go through and you put in 11 plus or minus 6 squared minus 4 times 24, which is 96, all divided by 12, these pop out, right? And those were in our list of possible P's and Q's. What you can do with each lower term is you can get rid of things that aren't part of the lower terms. So every time we get smaller and smaller in our degree of a polynomial, it gets slightly less options, and we weed things out. And so it's a weeding out process. It's a scythe. But notice I said some things about needing to know what our signs are. And so what we want to do is we want to find some way of determining how many positive answers or how many negative answers I have. And so that's what we're going to look at now. And let's go back to Descartes, the guy who invented the Cartesian plane. He noticed something about the signs of the answers and what happens when you get certain signs in the answers and how they react with the function. If the function's even or odd, or how many of these things go through. And so we're going to get another rule. I'm going to, let's see, I don't have much space left on the end here. I want to save this out. Give me a second here. I want this as a ping. And we'll go to a new one. We'll fill the board. Get a pen. All right, so things we are using. Things we use. That's a bit big. There we go. Things we use. So we use the rational root test to find possible roots. It's going to be the first thing we use. Taking all those possible fractions and seeing what roots we can get. We use the remainder theorem to test the possible roots. And we're going to use a thing called Descartes' rule of signs. To focus on which possible roots. And then we're going to use division to reduce the problem. So we get a list of all these possible rational roots. We list them all out. PQ, PQ, PQ. Oh, there's loads of them. All right, we'll take Descartes' rule of sign, and so many of them are going to be positive or negative. We'll test them with the remainder theorem. As soon as I get one, I want to start dividing. I want my problem to get simpler and simpler each time I look at it. And so this tends to be how we use these things. So I'm going to look at Descartes' rule of signs now, and we will have now a sufficient toolbox to deal with any degree polynomial and get answers for it. So Descartes' rule of signs. So I say that really excited. This is one of those things where I think studying algebra, algebra makes a sense. We have this unknown thing. What's the pattern going through? You learn these rules of real numbers. You manipulate things, and it does what it can. But then you start dropping down to these high-order polynomials, and you look at the graphs, and until you really get into some of the nuances of calculus, a lot of where these things are coming and why they change and bend really quickly are hard to see. I mean, you can see them, you can graph them, you can describe them. And so this toolbox of these things that Descartes, Leibniz, who else worked on these? There was a whole bunch of people working on this stuff that kind of led to some of what became the backbone of calculus, found for quick ways of finding solutions and solving problems. It became very useful. And once you see what's happening, you can understand the process, but I don't think it's intuitive. I don't think looking at a polynomial and its coefficients tells you a lot about what the solutions are going to be. I mean, we have those, hey, if it's a third degree polynomial, there's possibly 3 roots. Coming across. So it has to be at least one. It's an odd function, so it has to cross somewhere, right? If it's an even function, it might never cross, and everything could be imaginary. And so these tools are really nice tools. And I remember first learning Descartes' rule of signs, and I think I learned it all in a graphing context because we didn't have graphing computers, we didn't have graphing calculators, and all this was done as graphing exercises and very little of how it was used as a utility to solve, because that was the next thing you learned to take graphs to solve. And so I'm hoping that we can make this work for us. Again, I'm copying the book here versus how I would say this. So we're going to have some polynomial of x with real coefficients. So we're not worried about if they're integers or not. Now this does work with integers and the rational roots, so I wouldn't. This is a good thing to use with the other toolbox to limit things out, but it'll also give us information if we have real numbers coming out. And a non-zero constant. And I want to say something about that right well. I'll write this down. Again, this is on page 307 in the book. With terms in descending powers of x. Now they're rewriting this. This is the form we have been using. Remember I said we want to keep our x's go with the powers going down. Make those powers go down in x because it's going to tell us something. Well, this is what Descartes had to do. But he has to spell out, hey, put this in descending powers of x. I want to focus on something with a non-zero constant. What it means to have a non-zero constant. So I'm just going to write a 4th degree polynomial. 4x to the 4th plus 3x cubed plus 2x squared plus x. But we have 0 here, right? And we don't write our zeros. So I'm going to get my black pen. We don't write our zeros, so we'll make it go away. Well, we could. This isn't going to work for Descartes' rule of signs. This has a factor of x that we can pull out. And that's going to have a root at 0. And it's because this is dealing with positive and negatives, this root at 0 gets in the way. And so when you want to use Descartes' rule of signs, if you don't have a constant that is 0, factor out x. Factor out something about x so that you can then use it on this. And this now meets our definition for Descartes' rule of signs. And we've also got one of our roots out of the way, right? We know x equals 0 is going to be one of the roots or solutions. All right. So I just want to make that as that's what it means by having a non-zero constant. Is if we had a 0 constant, we have a factor of x, and that sits on 0, and it's neither positive or negative. And Descartes' rule of signs talks about things being positive or negative. So it's really important that we have that definition. All right, so there's 2 parts to it. So for part A, the number of positive real zeros or solutions or roots either equals the number of variations in sign or is less, I'm going to scroll this up here, less than the variations by even integers. It's a mouthful, so let's look at this. We're going to look at A, and we're going to look at part A. I'm going to do my examples. I'm going to change my colors for my examples. I'll keep the blood red or the weird glowing red for Descartes' rule of signs, and then in between A. What we're going to do, and this whole variation by even integers means we count by 2s. We count down by 2s, actually. So I will put in my new notation, count down by 2. And so let's see this in an example so these words can go back to what's happening. So let's look at the polynomial x to the fourth minus 6x cubed plus 8x squared plus 2x minus 1. So here's my polynomial function, and I want to know how many positive real zeros there are in it. So how often does the sign vary? Well, I start with a sign that's positive. This is a positive 1. I change to negative. That's one variation. I change back to positive. That's 2 variations. So there's 1, there's 2. I stay the same, and I change to negative. So there's 1 more. So sign changes, sign changes, sign stays the same, sign changes. I count up the changes. There are 3 sign changes. Well, that means there are 3 positive real roots, or I got to count down by 2, 1 positive real root. I'm either going to have 3 or 1. Notice I can't have 0. Counting down by 2, I don't get to 0. I have to have at least 1. That's good. That means when I'm going through that list of rational P's and Q's, I know I can test the positives and they're not all going to fail. There's at least 1. And so this says, hey, at least 1. Yay! I know something I didn't know before. It's always good to have a kernel of information. Because look at this. What are the roots to this? I can't see it in the polynomial. So I've got to use these tools and these tests to help chunk it out. I know, hey, look, I have a 1 and a 1. So my possible roots are plus or minus 1. At least one of them has to be positive, so I guess one of them is positive 1. It doesn't work though, does it? Yeah, it does. 1 minus 6 is negative 5, positive 3. Let's see here. I'm trying to put my positive 1 in. So that's 10. Yeah, positive 1 doesn't work. What's going on here? Oh, these are reals. Right? So we can't assume that our rational roots will always work. Real numbers might come in. But this does help us narrow down the list of rational roots. Right? See what I did there? I made an assumption, but these are possible rational roots. And this will help us weed out our tests. Because if we look back at that other test, there's a lot to do. And we want to weed out the test. Okay, so we can find positive solutions. This says there's at least 3, or there's 3 at most, 1 at least. And that's good. This 1 at least can help us track things down. All right, but there's a second part to it. This was positives. How do I find my negative numbers? So I'll come down to B here. Let's find my negative roots. And so the second part is the number of negative real zeros. The book uses zeros. I like roots. And of course, every time I'm seeing this now, I'm seeing Questlove on the Jimmy Fallon show. Go figure. Is equal to or less than equal to, sorry, the sign variations in P of negative x. I look at what happens if I put negative x in, or less, by even integers. So again, we're counting down by 2. And so I'm going to repeat the polynomial we had before, and we're going to look at how many negatives it could have. So to find the negatives, I want to put in negative x. Well, a negative to an even power is positive, so that'll stay the same. A negative to an odd power is negative, so that changes. A negative to an even power stays the same. So notice how I'm changing the sign of my odd powers and keeping the sign of my even powers. So if I were to drop a negative x into here, a negative to the 4th power is positive. If I were to drop a negative into here, a negative to the 3rd power is negative, and negative times a negative is positive. If I drop a negative into here, negative is positive, a positive times a positive stays positive. If I drop a negative into here, it's negative, and negative times a positive is negative. And so I've always looked at this after doing thousands of them, is change the signs on your odd powers. But drop the negative number in, drop the negative in, take the power and see what happens to your signs. It's a good way of watching this. Or watching this, no, what does it say? These patterns. I guess we observe the pattern and we find we kind of react, adapt, develop the muscle memory for how the pattern is. Well, this is positive, this is positive, this is positive, so no sign variations. One sign change stays the same. So one sign change. So this has one negative real solution. And what we learn from this is that this is a power 4. It can have 4 real, or what? It can have 3 positive and 1 negative when I combine the two rules. Or it could have 1 positive, 1 negative, and 2 of something else. Something else. Something else. What is that something else? So we have a series of tests now that can help us find roots. But what we don't really have is something that tells us where to stop. And that comes from the fundamental theorem of algebra. The thing that makes algebra work. And so the fundamental and it says if you have a polynomial f of x to degree n, with n being greater than or equal to 1. Right? And remember, when n was 0, it was a constant, and constant functions never cross the x-axis. And our definition of a root is crossing the x-axis. And so what this is saying is it has at least one complex 0. So as soon as you have degree n, you get complex numbers. Remember, our complex number has a real part and an imaginary part. Now, everything we were doing before for real parts, so real numbers, b equals 0. And that's still a complex number. It's still a part of the complex number. What ends up happening is n tells us how many roots or zeros the polynomial has, including multiplicity, right? So this thing here has 4 complex answers. They might be repeated, they might not. Now I know at least one of them, or 2 of them, are real, because one has to be positive and one has to be negative due to Descartes' rule of signs. The other 2 could be complex numbers. And so the fundamental theorem of algebra says, if I have a solution, that solution is going to have at least one complex number. If they are completely imaginary, though, some neat things happen. And that comes from, I'll scroll here. I missed the top of the page. I'll scroll up here. That's why. Let's say I got to the bottom really quick. When we learned our complex numbers, they had a friend, a conjugate. And the conjugate, when multiplied together, would give us this. Right? The imaginary part would go away. Now notice, in our polynomials, we don't have imaginary coefficients. I don't have a I hanging out in front of the x's. So if there's something imaginary in there, it has to be multiplied by something to make it go away. Wait. When I multiply these 2 things, the imaginary part goes away. So things with imaginary parts come in what we call conjugate pairs. So the theorem states this: if f of x has a complex 0, a plus bi, then its conjugate pair, which is a minus bi, is also a 0. Well, this means that we can start tracking what we need to solve equations. What are all of the possible solutions that we can have with equations? We can start keeping track of solutions. So I'm going to use the one we used down here, which was x to the fourth minus 6x cubed plus 8x squared plus 2x minus 1. So I'm going to bring that up there, and I'm going to put the fundamental theorem of algebra on top of the conjugate pair theorem, on top of Descartes' rule of signs, and we're going to look at everything we might see as possible solutions to help us keep track of what might be happening with this. So let me get this guy out here as we start looking at it. Where did x cubed go? There we go. So x to the fourth. So it was x to the fourth minus 6x cubed plus 8x squared plus 2x minus 1. So there are 4 possible solutions. So I can have complex with an imaginary part, I can have a real positive, and I can have a real negative. Now, some of these solutions might stack up on top of each other. They might have a repetitive multiplicity, right? But that'll still show in these. So these come in pairs. So I could have 4 imaginary solutions and no reals. Right? I could have 2 imaginary, 2 real positive, 0 real negative, 2 imaginary, 0, 2, 2, 1, 1, right? Everything that adds up to 4. And let's see. That's those 0, 4, 0, 0, 0, 4, and so on and so on, right? I do these repetitions. Well, let me write the whole table because I'm going to scratch some things out. So 0, 3, 1, 0, 1, 3, and 0, 2, 2. These are all my possible solutions of a 4th degree polynomial. I can have 4 complex with imaginary parts. I can have 2 complex with imaginary parts and 2 real. I can have 2 complex with imaginary parts and 2 negative real. I can have 2 complex imaginary, 1 positive real, 1 negative real. Right? All these things add up back to 4. Because these come in conjugate pairs, there's always an even number. But Descartes' rule of signs told me I have at least one, or I have exactly one negative. So it can't be this, because I need exactly 1 in there. Can't be this, because I need exactly 1 in there. And so anything where there isn't exactly 1 for the negative real, I scratch out. And I have 2 possibilities. I can have 2 complex answers, 1 positive real and 1 positive negative. Or I can have 0 complex with an imaginary, 3 positive real, and 1 negative real. All of these add up to 4, but because of these 2 tests, the first off, the conjugate pair says, hey, you're going to have 4, 2, or 0 imaginary numbers. Then we do Descartes' rule of sign that says, you've got exactly 1 negative. Well, Descartes' rule of signs crosses out all these other things. All right, I have babbled on for a bit. We have finished section 4 in the book. The homework is for section 4. We are starting section 5. We will wrap up section 5 nice and neatly, and that covers everything with polynomial division. And we are going to spend next week wrapping up section 5 and wrapping this all together, running these tests, doing the things that take you from section 1 all the way through section 5. Before we even start into anything later. We're going to tie all of this together because these techniques are great for breaking down into roots. And roots are solutions. Zeros are solutions. They're answers to problems. And so these techniques are really, really useful, especially when you have just data. This can take data into polynomials. All right, exam due the 12th. It's up on Blackboard. Someone noticed that it still had the 9th on it. I had updated the date. I'm not sure if that got messed up in the Pearson thing, and I thought I had saved it and it hadn't saved when they were resetting the servers, or if it was just one of those things. If you need anything, email me. The questions. I'm getting them through email. I'm putting up worked out examples. They're showing up on the playlist to YouTube for these videos. Billy, thank you for keeping me awake in here. Again, we have finished up to section 4 of chapter 4 in the book. We're starting chapter 5. I get really excited with this because these things look ugly. And sorry, I'm like all in excited mode, right? Because I look at this and what is it doing? What are answers, right? Where are the answers in these things? And it's like rock climbing, right? You have this sheer cliff that looks impossible, but if you can find little toe holds, little finger holds, little cracks and crevices, you can start crawling through. And the fundamental theorem of algebra sets that first crack going, hey, you've got to have 4 roots. They might be repeated, but you can have 4 roots. And they could be complex. Well, then Descartes' rule of sign goes, well, I can tell you how many are going to be positive real and how many are going to be negative real. Possibly. And so you can start throwing some things out. And then the rational root test goes, well, if it's an integer, I can tell you what it might be. And the remainder theorem says, okay, you can throw these things out. And then once you get one, you can divide down, and all of a sudden, it just collapses into something that's tractable. But that takes the practice, and we have to practice through the different sections to make sure that we get that. All right, be safe, be well. Email me your questions. If you need anything, I am here. And I guess I'll do the same thing I did to the other class. I gave them a musical outro, so you guys can get a musical outro. We'll go with Soft and Gentle. I think it's that.